Okay, so we're looking at quiz 2, 212 spring 15, chemical kinetics. Shh. We're in a process. Okay, for number 1, okay, just for argument's sake, we'll review the question. It says, for the reaction of 2NO2 going to nitrogen monoxide and oxygen, the concentration of nitrogen dioxide, the reactant at time 0 is 0.1103, and at 60 seconds is 0.1060. And so the reason I gave this is because a number of you struggle with the concept of rate averaging. And so it's the same problem, different numbers. So for 2NO2 as a gas, going to 2NO as a gas, plus O2 as a gas, concentration of nitrogen dioxide as a gas. I should put gas in there, but that's all right. At t equal 0 seconds is equal to 0.1103 mole per liter. And then at 60 seconds, NO2 gas at t equal 60 seconds equals 0.1060 molar per liter. And so to get the rate average, it follows simply the definition of what rate is. That's the change in concentration over time. So that is change in concentration of the item of interest, and that will be typically in moles per liter over change in time. So that would be, we're going to this one, that's 0.1060 mole per liter minus 0.1103 mole per liter, such as our numerator. Change in concentration, and 60 minus 0 is 60 seconds. And to save us some time, I got minus 7.2 times 10 to the minus 5 molar per second as the rate average, and that is C choice for those keeping score. Any questions? Okay. Yes, you will see this on the major exam, just as you saw it here. It'll be an equation and some different concentration numbers, but it's still worked in the same context. You should do well. Okay. Okay. I'm going to scoot this up. Okay. For question number 2, consider this reaction given, ammonia, oxidation of ammonia, if you will, forming nitrogen monoxide and water. If ammonia is disappearing at 0.5 mole per liter per second, what's the rate of appearance of water? Well, I think everybody can identify water, hopefully. And so this is a question by which we set up a pair of rate relationships, and it swap coefficients and set them equal. Okay, the bigger number is doing what it does faster than the smaller number. So in order to make them equal, you swap the coefficients. Think about that. Okay, so for number 2, we have 4NH3 as a gas plus 5O2 as a gas going to 4NO as a gas plus 6H2O as a liquid, and the change in NH3 gas over change in time is given, and I might write given just for interest, is equal to 0.50 mole per liter second. And the question is, what is the rate of appearance of water? You know, you can write a relationship from an equation in terms of the coefficients like this. So if you take change in ammonia over change in time, you can set it equal to the change in H2O over change in time. Isolate those with brackets. And if the coefficient for ammonia is 4, you can put it over here with water. And if the coefficient for water is 6, you can put it over here with ammonia. Now you have a linear equation and one unknown. Okay, and you solve for the unknown. The question is, what is water? And you're given the 0.5 mole per liter per second, which you put in there. So our change in H2O liquid per unit time, now if we solve for that, it's 6 divided by 4 times the change in ammonia over change in time, like that. So it's 6 over 4 times 0.50 mole per liter second, and I got 0.75 molar per second, or 0.75 mole per liter second. Now that's just to emphasize the units sometimes come up in the problems in terms of moles versus molarity. So please double check that and your work, and that comes out as D. Everybody comfortable with that idea now? Items are set up in pairs, swap coefficients, that'll make it. Okay. Okay. On number 3, where's my, there it is. Number 3 was simply a definition based on the work we've done in the lab. I asked you about accuracy and precision. So it's very important that you learn how to present data. If you run a series of experiments, all the data is collected the same way, then you want to take an average and talk about the variation of your results about that average. Okay, so number 3 is for data series collected in same way. That's simply okay. We can say you'll have 2 kinds of error evaluations. One will be an accuracy analysis, which by definition is the variation about variation of data. I'm going to go ahead and put it in data. And is typically in percent error. Okay. Precision, by definition, is the variation about an average. And and this is typically represented as an average plus or minus standard deviation, which is a 68 percentile region, or in the one that I'm giving you, average plus or minus a confidence interval. And if the number of trials is less than 5 trials, you would more than likely deal with it there. If the trials, I'll make a note down here, note, if number of experimental is less than or equal to 5 trial experiments, use average plus or minus the confidence interval, and the confidence interval is approximately 2 times the standard deviation. And that's what we were showing you. If the number of experimental trials is greater than 5 to 10, some people will still use it up to 10, use average plus or minus the standard deviation. And it represents the most widely used error representation of a set of data where you've run 15, 20, 100 repetitions and so forth. They'll get a standard deviation of that data. Okay. So the variation of data about an average is, of course, the precision is the answer to the question that we're working with. Okay, the next one, you're given a reaction, hypothetical reaction, that was found to be first order in A and second order in B. What's the overall order of reaction? So number 4, given A plus B goes to AB, and reaction is first order in A and second order in B. Now the numerical rate law, assuming you have K, you've already figured it out, rate equals K, which is assumed known. A is to the first power, and it was understood to be a 1 right there, and B to the second power. So when we look, now if you don't know this, listen to me. The exponent says is an order of reaction, is how that reaction trend changes as a function of that individual component. The order of the reaction with respect to A is a first order. The order of reaction with respect to B is a second order. But the overall reaction order equals the sum of exponents. Just add them together. And so that would be C choice for our brethren in school. If you didn't know that, I might encourage you to go look at the video on the material that we covered when we were writing those rate laws and talking about how the rate laws of the reactions change. Finally, I gave you a little problem similar to the problems we worked the other day. Okay, based on the following data for the hypothetical reaction given here, which of the following rate laws the reaction? Well, the K value I set in there as a known in terms of the answer choice. You should have seen that. So it was a matter of using the data to determine the appropriate orders of reaction. And I left the material on the board over there for you to use if you wanted to look at it. That was fine with me. The idea is to learn material. So if we take an experiment, one, two, and three, and component A against component B produces a rate in molar per second. We have 0.10 molar, 0.10 molar, 0.20 molar, 0.10 molar, 0.20 molar, and 0.10 molar. So you're changing things and then see what happens. Okay? Usually one of the first ones, you'll have in your collection a reference rate. This is 10 mole per liter per second. Then I had 20 mole per liter per second and 40 mole per liter. I try to keep it, reasonably straightforward for everybody to use. Now, what do you deal? How do you deal with this? You hold one constant, one of the components constant, vary the other component, and if you have three components, you hold two components constant and vary the individual ones. That if you look in your textbook, or if you have one, you'll see some problems that have three components. And it usually doesn't get any more complex than that. So here we're looking at holding this one as a constant, and we varied this one by doubling the concentration of B. And the rate change was also 2 times. So if you double concentration, you double rate, what's the order? First order. Okay? The trend is a first order reaction. So this is a first order reaction. That's the conclusion that you should draw from the experimental observation. That's why you're going from empirical to numerical. Now we hold the B constant and vary, I'll put it on the other side, the A right here, and then we observe what happens here. This jumps by 4 times, and that means what kind of order? Second order, right. So we have a 4 times increase with 2x concentration. Your conclusion is second order reaction. So when we write the empirical rate law for this relationship, the empirical your job is to find out what x and y are. So by doubling A, holding B constant, and observing what happens when it's a second order reaction. And B, we held A constant in this context, and we double the concentration here, double the rate, then that is a first order, so we put a 1 in there. Of course, I gave you the K value, so the numerical 10 to the minus 5 molar minus 1 seconds minus 1. So there's your rate constant, and you put in A squared B. So this is the numerical without the 2 and the 1 scribbled in here with just Y's and X's. That's an empirical. And they're only determined how? Experimentally. Thank you. Yeah. B choice for those keeping score.